My name is Erik and Andrejko. I've been a data scientist, I guess, officially for about 10 years now. But as I was reflecting back yesterday, I realized that I did my first data science model about 20 years ago. Of course, it wasn't called data science at the time. I thought I was just solving a business problem using statistics, but I was doing a little bit more than that. So I worked in data science applied to lots of different areas. I've worked in e-commerce, I've worked in agriculture. Currently I'm working in food and nutrition. And I wanted to share with you a couple of different things. One way to think about this is 10 lessons I've learned, I guess, over 10 years. The other way to think about this is 10 mistakes I've made. So if you listen to this, you can avoid at least 10 big mistakes, and I'll share some stories of some of the big mistakes I've made. And also, I want to encourage you to have kind of a broad perspective. So how many people in this room are data scientists, just so I have a sense? Okay. How many people are software engineers? All right. So what I don't understand is everyone who raised their hand for data scientists is not raising their hand right now. Because data science is a lot like software engineering. It's not exactly software engineering. But if you believe the Drew Conway Venn diagram that was actually on the slide here yesterday, everyone who's a data scientist is doing some kind of software work. So although it's not exactly software engineering, I want to encourage you to think about it as software engineering. I think there's a lot of lessons that can be learned from software engineers that are very applicable day to day. And I think 10 years from now, if you forecast forward to the future a little bit, we'll see software engineer and data scientists probably become one thing. Companies like Google describe themselves as AI first. And what that means is that every software engineer at Google is encouraged to build models or is building models, quite often deep neural networks. So if you're a software engineer, you don't think about yourself as necessarily being distinct from data science. So that's one thing I want you to think about. The other thing I want you to think about is there are lessons from outside of kind of the software technology world, and I can include some lessons from architecture. And when I say architecture here, I don't mean software architecture, I mean people who build buildings or design buildings. And there's a great book which partially inspired this talk that I would encourage you to read called 101 Things I Learned in Architecture School. And you'd be surprised at the number of lessons that you learn as a data scientist from other disciplines like architecture. And in particular, one thing that I think is really important is that architects have a very broad mindset. They're designing something for someone that is going to live and exist in the world for a long time, in the case of a building, and it's going to be a very long engagement with the client. And the architect is not done when they design the plans and they throw it over to a contractor. They don't disappear. They're project managing it to completion, and then when the customer is in the building itself, they're working with the customer at refining the design or extending the design. So it's a very long-term engagement, and it's a very end-to-end engagement. So I would encourage you to think about that as well. So let's start with mistake number one, or lesson number one, which is to solve the right problem. And I would encourage you to understand the business case very deeply, and don't take what you're given as gospel in terms of what the problem is to solve. So when someone comes to you and says, I want to solve this problem, the first question or first response you should have to that is why? What are you trying to do? Suppose you had a solution, what would you do with it? Why is it important for the business? And the better you understand the business context or the context of use, the more easily you're going to be able to frame the actual problem that should be solved to one that's going to be important. And the big lesson here is to uncover the real needs or to uncover the real impact. Let me share a story with you. Many years back, I spent months building a model for recommendation system for a particular application. And I had a whole bunch of data. I built some great models. I built a whole data engineering pipeline. It was primarily just me and one other person working on this. And I built a pretty good recommendation system. It did ranking. It had good AUC in this case. It was deployed out into the world. And what do you think happened? Everyone was ecstatic and happy, or there was a problem? Well, there was a problem because What I hadn't done, and what I strongly encourage people to think about doing now, is I hadn't actually considered the economic or mathematical framing of the application. So if I had spent a day or even 2 hours on a whiteboard with some math or even in a spreadsheet, and assumed I had a model at a particular AUC, and I modeled the application of that in a business process, I would have quickly seen that this particular application, it doesn't matter how good the model is, because the ultimate financial impact would have been quite limited. And I probably would not have spent all that time solving that problem. I very likely could have spent that time solving a different problem, a better problem. So since that time, I now, especially when solving problems that are abstractly connected to the ultimate business use case, I actually build models first to relate the model I'm building to the ultimate business impact. These are primarily economic models. And that way you can ensure that you're solving the right problem, and you also understand at what point you get diminishing returns. The other strategy that relates to this in solving the right problem is to begin small and begin with something very tractable. So if you spend 4 months, go away and spend 4 months and come back and deliver something, that's a big cost, a big sunk cost to make up for. If you go away in 4 days and come back with something that you can quickly prototype, something very practical, you can uncover that you're solving the wrong problem very quickly. And in particular, this is a message that should be well known amongst engineers. How many people know what the Agni means? What is, okay, a few people. So what does the Agni mean? You're not going to need it. So as people who build modelers, or people who build models as modelers, we need to think about, ultimately we want to have impact. And it's very easy to always take the next iteration of the model. Yeah, I could use a different technique. I did a random forest, I can try an SVM. I tried these features, I didn't try these other features. There's always some marginal change you can make. But quite often you don't really need it. And remember that. So that's solving the right problem. Lesson number 2 is to make sure you understand the data. And this is actually a quote from somebody, some of you may know, named Ronald Reagan. When Ronald Reagan was dealing with the Soviets, this is the quote that he used, which is, you should trust but verify. And if there's one thing you remember from this talk, it should be this quote. This applies to data in particular. So when you're given a data set, you should trust that it is as it's described, but you should verify that. And one way to verify that is to do EDA. The first step when given a data set should always be to do EDA. Is that what everyone does now? Does everyone start with EDA? Yes? It's certainly yes if you've been burned many times. And the best way not to be burned is to do EDA. And the second way not to be burned is to what I call use the source here. Is to go back to the source of the data, and sometimes it's multiple sources of the data, and ask questions. So there's one woman I remember on a team I used to work with who was very, very good at this. Every time she was given a problem, she would look at the data set and spend usually a day or two looking at the data set. She would always find at least 3 major problems with the data. Doesn't matter how many people looked at it before, she would always find those 3 problems. Then she would go back to the source and she would uncover, well, actually they changed the instrumentation process at this point in time, so that's why this variable changed very slightly. So we need to actually normalize at that point in time for it to be commensurate. So be that person, the annoying person who finds problems in data sets, goes back to the source and asks questions, and then deals with it. It will save you a lot of trouble after. Next lesson is to declare intent. So before you do something, have a clear plan about what you're going to do and communicate that plan. This I've seen work well in very formal settings and very informal settings. So an informal way is to just tell the stakeholder what you plan on building and what you plan on delivering and when. That's a very informal way. And then there are more formal ways to do this as well, which is to have a formal plan where you define up front what data you're going to use, what methods you're going to explore, what you're going to deliver, etc. So set expectations, communicate your plan, and as you go about this process, you need to think about yourself as a product owner in doing product development. So you have some customer, and you need to manage that customer's expectations in terms of what you're going to develop. I'm curious, how many people as data scientists work with a software product manager, or someone like that in that role day to day? A few, but not everyone. So for the people who don't work with product managers, who are essentially voices of the customer and kind of defining the business problem, I guess that means you are the product owner, the product manager, because the need for the role doesn't disappear because there's not someone in the role, but you're going to have to fill it. And one of the important things that you need to do in terms of this role as a product owner is you need to be very clear in terms of defining success. It's much better to define success, and in particular to define how you're going to measure model success early in the process rather than later in the process. That avoids all the temptation to change it because you realize that it would be better to measure it one way rather than another, and allows you to also begin to socialize the ways in which you're going to communicate if a model is good or bad with the right audience in terms of the metrics. And as you're going through this development process, think about managing risk and failing early and failing often. So this is a communication and stakeholder management activity. Okay, the next lesson. So now this is going to get a little bit more technical. So far it's been more people oriented. Now we're going to get a little more technical. There is no power like versioning and replication. The most important thing about replication is this, which is that consistency builds trust. So when you are delivering some answer or some model, if you can reliably deliver the same answer and the same model and the same results when needed, that creates a tremendous amount of trust. The converse of that is also true, which is if you change your answer multiple times, you deliver different numbers. If you go back to someone who's using your model and you say, oh, sorry, the number I gave you yesterday is slightly different today, but it's better today. You can't do that too many times before you erode a lot of trust. And there are some strategies that can be used to build this kind of reliability. So first strategy is make sure you're versioning your code. I'm going to assume that everyone is using some version control system for code today. Is that true? Yeah? Okay, good. That's kind of a bare minimum. Is to at least version your code so that you know what form the code was in at what time. But there are a bunch of things on top of that that can be done as an artifact of doing code versioning. And that is, you can do code reviews. So this helps to build consistent, reliable results, and to avoid defects is to actually have code reviews done. How many people here do code reviews of their code today? A few. Okay, that's good. Every time I ask that question, the number of hands goes up, which is good. In addition to reviewing the code for bugs and defects, you can also review the code in terms of appropriate methodologies, and also view the code with respect to appropriate dependencies. So versioning code, I would say, is essential. And we have enough tools to do it today very easily. The next is a little harder. Version data. So it's not enough that the code be the same to deliver reliable results, right? The data input also needs to be the same. The simplest way I know of to version data is to build functional data pipelines. By functional, I mean that the output of the data pipeline is completely dependent on the input of the data pipeline. And so if you have a functional data pipeline, then your data is all immutable, right? And you can easily then reference the data that, a data artifact, and it won't change. So if you run any code on top of that data artifact, the output of that will be the same later. Now this is not easy to do, and you can go way overboard in engineering systems for data versioning. And your primary problem is not probably data versioning, so don't over-engineer this. This can be a Yagni moment, but it does need to be done. And then if you do that, it's very easy to then version models. And one thing that I recommend is to think about models versioned as containers and build them as artifacts. How many people in this room are using Docker, for example? Okay, many. So Dockers are a pretty cool technology for those who aren't familiar. It allows you to collect development dependencies like libraries, source code, and data together in a single artifact. And then you can treat that artifact as an immutable block box. So that is your model. It has everything it needs to live together in a single unit, and it won't change over time. It's an artifact that's immutable. And this makes it very simple to do testing and evaluation, because you can send your artifact into a testing system like a CI/CD system, which we'll talk about in a minute. You can very easily do model comparison. If you have the model that you built last week and a new model that you built this week, both artifacts exist. You can interrogate both artifacts together, and you can compare them for doing model selection. And perhaps most importantly is that it's very easy to release your models into the world, because they're already there as artifacts and they can be run on some container orchestration system. And I strongly recommend using CI/CD as a data scientist. So CI is continuous integration, and CD is continuous delivery. What that means is that when you release new things like new model artifacts, they are integrated into some system where they'll be used immediately, and there is some level typically of automated testing that's happening on top of that integration. So if you are working as a software engineer, this is a very common practice. You will do this all the time. If you are delivering as a data scientist models into a production system, eventually they will touch some CI system. And so if you adopt that practice earlier, it will be easier for you. And then think about doing the step above that, which is continuous delivery, which is if you have a robust testing system that is testing your model artifacts as they're being deployed, you can very easily ship them into some runtime environment as a continuous deployment process. And this can be completely automated. So the latest version of your model gone through this testing system is now running. If you are doing this very well in production, if you are a little bit more risk adverse in some production-like environment. But this allows you to very reliably deliver consistency to the actual runtime environment. This is more some practice considerations, which is lesson 5 is automate and iterate. So the first is learn tools and use them. Some tools that I think every data scientist should know. One is the command line, scripting, the bash, those types of things. Certainly whatever development environment you're using, Python, R, probably, you should know those very well. And other tools like Domino as an example. There's a variety of different tools, increasingly large number of tools that are available as data scientists. And you should use them, integrate them with other tools that you're adopting, and you should adapt them to your use case. Now notice I didn't say here build a lot of tools. So that's a last resort. I think increasingly there's less and less of a need as data scientists are served better by a marketplace of tools to build our own tools. And remember, anything you build, you're now committed to maintaining. And anyone new comes in the organization will have never used that tool before because you built it. So it'll be new to them, so they have to be trained on it. So those are all kind of costs of doing big business. And fundamentally, think about yourself as a data scientist as being in the business of automating away your job. So anything that you're doing manually is probably, especially something you're doing manually repeatedly, is not a good use of your time. So automate it. And since you have all those tools that you know, it should be very easy to automate these things. Also, think about this from a business owner perspective. What do you think is the right business choice? Saving an hour of your time and using 1,000 hours of compute time, or the reverse? Well, you know how much you make. So you can do the financial trade-off. 1,000 CPU hours is not that expensive compared to what most data scientists make. So you should be thinking about how do you maximize the effectiveness of your time. And there's some particular things that I want to encourage people to do that are directly related to automating away yourself as a data scientist. And now this is where I may say some provocative things if I haven't already. So you feel free to disagree with me. So one thing I'll say is that I'll relate a story, which is a friend of mine. He's a great data scientist. He specializes in doing time series models. So complicated time series data come in, and he spends all of his time as a data scientist building beautiful features on top of those time series. Compressing the time series of summary statistics, getting some nice feature, and then putting those features into models to predict some outcome of the time series. And he told me that he used to believe that as a data scientist, he was fairly immune from having his job automated away because he was the one building all these automation systems. And that he had all these beautiful intuitions about how to deal with time series and how to build great features from time series. Until one day he started building models using DNNs, and in particular using RNNs, which take a raw time series and predict the outcome better than he could do with all of his feature engineering. So then he said, well, I witnessed my own replacement with the machine, and it's something that you should embrace. So I would think about your activity as a data scientist as not being in the business of feature engineering, because I don't think that that's a long-term competitive advantage as a data scientist. So delegate as much as you can all of your feature engineering to something else, like another model. And this means, in particular, select features automatically at a very minimum. And then the other trick I want to share is to very strongly consider using representations in lieu of building features, and especially engineering features. So by representations, what I mean is you can take a large data set, you can fit an unsupervised model in some way on this large data set, like clustering as a classic example, and then use the output of that unsupervised process as features. So rather than handcrafting features, you've delegated that to some other algorithm. In my experience, deep neural networks do this very, very well. If you've ever seen anything with deep neural networks around compressing images to kind of semantic feature vectors, for example, and then training models on top of that for some other use case, you can take an off-the-shelf trained image classification model that you download off the internet. You don't even really need to know much about how it works. You run it over the images, say you have, you get a bunch of vectors, and then you use those vectors as input to your model instead of handcrafting features, and you can get extremely strong performance gains in practice doing that. So those are some tricks I recommend. So that's one way to kind of make ourselves irrelevant. And the other major strategy here is to delegate model tuning. So that's another thing that I think data scientists think that is their job, which is my job is to know which models to build and to select hyperparameters for those models. So yeah, maybe I no longer do feature engineering, but now I'm a tuner, kind of like a Wizard of Oz type person who tunes things. That's another activity that you probably shouldn't be doing. Compute is extremely cheap. It keeps getting cheaper. We keep getting more and more sophisticated CPUs, GPUs, etc. And so you should just be using them to select hyperparameters. If you have a great model selection process, which you've already defined up front and you've already articulated, you should use it and use compute instead of doing model building. And then the other thing I'll mention here is that it's great to recognize diminishing returns. Done is always better than perfect. You never want to deliver a perfect model. Now, this is one other trick. One way you can certainly have yourself be out of work is to deliver a perfect model, so don't do that. You always got to save a little bit of work for yourself to come back to and do later. And make sure that you are delivering models that are 80% good enough. Okay, so the next big lesson is to own quality. And this is kind of a big lesson, say, from architecture. How many people have data science QA teams that they work with? Okay, so I saw one hand go up. So what do you think that means for the rest of us? Who do you think the QA team is? Yeah. Look in the mirror and you'll see the QA team. So you are the QA team for your models. And that doesn't mean that it works on your machine and it works over here on your data set. That means it works over here in production. So how do you make sure it really works? So at the very beginning, or very minimum, is you need to do backtesting and cross-validation. So this means that you're testing models against data you already have. Now, if you're really thinking about this from a QA perspective, you're not doing backtesting and cross-validation in a way that makes it easy for the model to do it. Or is convenient, because I have the data segregated this way, so it's convenient. So do this very, very carefully, so you don't confuse yourself. You want to be very, very skeptical of your own models. Make it hard for the model to be successful. Make sure that you're replicating, you're doing backtesting in the real business context. And this is where it's very handy, in my experience, to have statisticians on staff. So a statistician, I'll define this way in this context. A statistician is somebody who, after you've just tested your model, has a problem with the way you've tested your model. So you want those people to be around so they can point out the flaws in what you've done. And in particular, you want to be extremely skeptical of everything. Verify, trust but verify, especially for your own models. Question everything. If your model performance looks too good to be true, guess what? It's too good to be true. And the warning I'll leave you with related to this is target leaks happen. So everyone is familiar with a target leak? How many people have never had a target leak happen? Anyone? All right, good. So everyone has had it. The only people who have not had a target leak happen are the people who don't know they've had a target leak happen. There's another multi-week period in my life that I can never have back related to a target leak, where a model was built, it was tested, it seemed a little too good to be true. The person building the model was quite happy with it. All of the domain, it was a model in a particular domain, just let's say, I think, predicting when farmers plant crops. You could explain it very easily to a farmer, it made sense, it was all perfectly logical, except it had a target leak, an extremely subtle one that we finally found. So another big strategy to ensuring quality is to use simulation. So by simulation, I mean you should take your model and input a bunch of data, not just the data you're backtesting with, but all of the conceivable data. You can think about it like fuzz testing if you're familiar with that, and simulate it. So what are you going to get out of this model if you throw a bunch of inputs into it? Do you always get reasonable things, or do you not always get reasonable things? Does it have the right marginal dynamics? If this input variable increases, does the output variable increase in the way you expect? This is tremendously important to do, especially when you're composing models. Because when you have model A, B, C, D, and E, and in complex environments you typically have 10 layers deep, the emergent behavior of the system is not going to be easy for you to predict. Even if you are a pro at partial differential equations, for example, it's still not easy. I mean, this is just chaos theory. So simulate it and measure it before it gets to production, and you'll see what it does, and you'll find errors with it. And then don't be afraid to use heuristics. So by heuristics, I mean the things that we don't like as data scientists is like, my model, it makes this mistake in this class of things. That's okay, well, put a business rule on the end of it to fix that class of things, and then it's fine. Safety nets are allowed in models. You use them, don't use too many of them, but certainly don't be afraid of them at all. Okay, 7, communicate and deliver. So remember, when you say you're done, really mean that you're done, not that you're going to go, not that you're 90% done. Here's a lesson from architecture, is that in architecture, the saying goes, it takes 90% of the time to be 90% done, and it takes another 90% of the time to finish the last thing. I think the same is true in data science. Make sure you deliver the right product in the right form. Not everyone is going to need the same thing. You can deliver APIs and services. That's very easy, in my view, to do with Docker. You can deliver data at rest, in which case you want to think about your batch computation pipeline and how your data sets will be used and integrated. And you can deliver applications and reports. So make sure you deliver the right thing to the customer. While you're going through the development process, again, communicate proactively. Discuss what you're doing as you're doing the work. Document it for yourself, if no one else, but especially for other stakeholders. Never underestimate the power of a demo in terms of getting early feedback, and ultimately deliver. So again, set expectations, make sure it really works. And then one thing that I don't see enough of, I think, at least in my experience, is make sure you collect feedback when your model is beginning to see the light of day in terms of being deployed. So how many people always have a feedback mechanism where someone who sees the model output can flag it as wrong, change the model target variable, or provide some other type of feedback? Okay, few people, only 2 people always do it. I don't always do it, but I should always do it. Because there's nothing more valuable than getting feedback in the actual real context of use. And so this is where it helps to be thinking as a product owner is you should make sure when you're thinking about how the model will be deployed, you're considering this feedback channel as very important. Okay, how many people have dedicated DevOps or SRE data science teams? Okay, a few. So for the rest of us, what does that mean? Who is the DevOps or the site reliability engineer person for your models? It's the same as your QA person. That's you. That means who's on call when the model doesn't work? I guess that's you too, because that's what SRE people do. They're on call. So you own operations. You may think about yourself like a chef. It's not enough that you cooked it well. It's got to go on the plate well, and the customer ultimately needs to be happy, or they're going to send it back. So some strategies that work well for this are to proactively monitor. So collect data in real time about what your model is getting as inputs, what it's getting as outputs. At the very least, summary statistics. Monitor how long it takes for your model to make computations, how many errors are happening. Report on this from your monitoring system and ultimately alert on it. I will tell you from experience, it's much better for you as the data scientist to notice your model is wrong than for someone else to tell you it's wrong in production. Again, trust but verify. So think about things like automating training, doing continuous testing, and doing continuous deployment to catch defects earlier in the process rather than later. And I would say be very, very prepared. Non-stationarity happens. So the inputs that you have to your model today will not be the inputs you have to your model tomorrow. So have mechanisms to at least detect that, ideally to mitigate that. I think things like multi-arm bandits, or if you have a rich online testing environment like your Byte ads, for example, and you have multiple models that are out there, and then you kind of have a layer that is watching the model performance. When non-stationaries happen, the bad models can fall out of the pool and you no longer see traffic, for example. So that is a great way to do it if you have that luxury. At the very least, you should have a detection system. Now, there's some more longer-term things to think about. So think broadly about not just solving the problems that you have now, but solving the problems of the future. And one way to do this is to think about decomposition. So think about how you're decomposing the world. So presumably you're not building just a single model and you're done, right? You're building models that are related in some way. Maybe they're compositions, they're connected to each other's. Perhaps they're in a service-oriented architecture. So think very carefully about how you decompose this over time. I'm not saying go and build a big upfront architecture that you then roll out over 16 months, because that will for sure be wrong. But the more mature you understand the space, then the more you should think carefully about how you're decomposing it, so that you can build composites and avoid monoliths. And ultimately, you're going to be very effective as a data scientist if you can create opportunities. So there's a mode of data science where you're reacting to requests coming in, you're reframing them like you talked about, and you're delivering results. That's a great mode to be in. You're creating value in that mode. And there's another mode where you're creating opportunities that people are not maybe even realizing or thinking about. That's an awesome mode to be in as well. And that comes from thinking about the way in which you're solving the problems and the capabilities you're building more broadly. You want to solve today's problems. You want to anticipate, because you kind of know where things are going and you understand the business case, what's going to happen likely tomorrow. And then you want to surprise people next week or next month or next year. And if you can do that, it creates a tremendous amount of value and also creates a tremendous amount of job security. And then think carefully about kind of continuous process improvement along these lines. So the thing that got, the style of data science that got you to where you are today may not be the style that will get you where you need to be tomorrow. So that's things like, are you doing online or batch model training or development? Are you using the right methods and approaches? Do you have the right processes and workflows? And as the tools and the ecosystem changes and the use case and context changes, all these things are going to change. So you should be continually reevaluating them. And finally, here's a couple of big ones that I don't see done enough. So how many people have a data strategy, by which I mean an articulated mechanism by which the data you're using will be improved over time? Okay, not very many. So here's one thing I'd like the rest of you to think about is that don't take data as given. And there's no data like more data. So when you go back into your day-to-day work, what are you going to do to develop a data strategy so the data you get is always going to be improving and you're going to be able to build better product on top of that? Think about that. And also think about serving multiple customers. We talked about kind of customer stakeholder management a little before, but you have multiple customers. There's the customer you're serving today, kind of the business, and the customer you're serving tomorrow, which is the business customer. But also you need to serve yourself with this. What are you going to need in the future? And what is your team going to need in the future? So make sure you're building systems that are going to serve those multiple. And then finally, think about this as a long-term game. It's not a single play game. It's a multi-stage game. So think about what you're delivering as capabilities and not just products. And think about the power of compounding as a strategy to get the delightful deliverables for the future. And think about this capability building as not just in a technology perspective, but from a team perspective as well. So think about developing your talent, which includes yourself. And you have to pay down technical debt as part of that development, and then you have to empower and stand back. And if you do that, you can typically see that there becomes a flywheel that gets started, and the whole process can ultimately sustain itself. And through this, hopefully, you're having a lot of fun. So hopefully, there were many takeaways for many of you. Everyone is probably at a different place in terms of their journey. So here are 10 mistakes I've made, and hopefully 10 things you can learn from my mistakes. So thank you very much.
We found, I know you had code review in there. Have you found it to be effective? I found it to have limited value. How would you go about making a code review effective?
Well, the most important thing I found is you have to define the objectives of code review.
Yeah.
So, and it depends on your context. So sometimes the code review is, there's a mentoring aspect. So there's a more junior person who is learning about the data sets or learning about past work. And so if that's an objective, that can be effective. If it's primarily to detect defects, it can be a little harder. Yeah. So what I found is talk to the team and define what do you want to get out of code reviews, and create some agreement about what you want to accomplish. And be pragmatic if they're not really working. then you don't need to do that.
Have you come across any strategies that you can recommend for labeling the data as part of the data strategy?
For labeling as part of the data strategy? Well, one thing that's very helpful if you're in a data-rich environment is to have a data catalog. And the data catalog can be richly labeled. So I don't know if that gets to your question in terms of labeling the data, but if you get to a point where you have a data discovery problem, having a data catalog is a great thing to have. And there are lots of tools to support this, although there's probably no standard one at the moment. So that would be one thing I would recommend. And then the other thing is if you have a good documentation system, which could be like a literate documentation system, like say using Jupyter Notebooks, that creates its own kind of data catalog. If you can search through the code, you can see what is referenced, even in advance of a formal system. And that becomes kind of a data labeling activity as well. Yep.
So this is a quality question. How do you think about model quality in an environment where you don't have ground truth? So where it is not a training set and a test data set, but rather where you're creating customer segments and when there is no one right answer?
Yeah, well, there's a whole strategy around incorporating subject matter expertise. So in that kind of use case, what comes to my mind is there's probably somebody who is going to consume this model. So you have customer segments. The customer segments are not just going to go out to the world on their own, presumably. They're going to be used by, say, a marketing organization. And so the marketing organization probably already has some prior beliefs around this. They already have some intuitions. And so they can act as subject matter experts. And you can get qualitative feedback from them, or you can get more formal crowdsourced feedback from them. And so where you are data poor, and this is something you consider for your data strategies, think about human in the loop type processes, either from crowdsourcing or subject matter experts, to generate ground truth labels. And then the other way I guess I would say about it is you may not have ground truth for kind of the intermediate output, which is customer segments, but if those segments are good and they're used to direct, say, marketing spend, you should see business ROI. So if you can connect it to some ultimate kind of business impact, that's another way to do it, but that's less direct and sometimes harder to measure. All right, well, thank you very much, everyone.